Okay, so what that means is that when I substitute this u into this a, what I get is three types of terms. One type of term is the left boundary condition. I get u0, which is a known boundary condition of a h0 hj. Okay, the second term is a summation of ui. I goes from 1 to n minus 1, the interior points of a hi hj. The third term is the right boundary. So the bilinear form gets split into the known terms and unknown terms. And I keep the linear form. So what you can see is that this is the unknown part that is going to factor into my matrix. This is my A times U. And my B now contains both the L and the boundary terms. So let me color this by saying that this is my matrix term, and this and this becomes my right hand side.
The one just below that, it's the J, and so is the H supposed to have J, or is the B?
Oh yeah, this is supposed to be J. Thank you. Thank you. Yes. Yes. All right. Okay. So now if you think of how you construct this matrix, remember our matrix A could have been constructed by our Aij is just the A of Hi Hj, right? So what we can do is we construct this matrix as just a bigger matrix containing with the indices I and j goes all the way from 0 to n as opposed to going from 1 to n minus 1, right? And then these two terms are simply u0 times one particular column of the matrix. This un term is another un times another column of the same matrix. So what this Dirichlet boundary condition does for you is that it simply takes two columns of the matrix away from the left hand side and move them to the right hand side, because you already know what is multiplied on these two columns, right? And then the fact that you only need to test the weak form on hj's corresponding to the interior nodes allows you to just remove two rows of the matrix. So the two columns corresponding to the boundaries gets multiplied with known numbers and moved to right hand side. The two rows of the matrix just gets removed, and then you still get a square matrix to solve. Right, so suppose you get a matrix A, this is 0, this is n, this is 1, n minus 1. So basically, you times u is equal to my B, my L, right? So let's say this is my L. So first of all is that I already know what is u0, what is un. So the unknown is only on this part, right? So that allows you to multiply u0 with the first column and move it to the known part. un gets multiplied to this, gets moved to the known part. And then you can remove the first row, remove the last row, because you don't need to test your equations with respect to the first and the last basis function. All right? So that's how you deal with non-zero Dirichlet boundary conditions in finite element. Yes?
Oh, sorry. So basically what you did is you moved the boundary condition to these source terms?
You can say it's source terms, but what do you mean by source terms?
Oh, like you said, you just moved them to the right-hand side, so I'm just thinking like, oh, it felt like you just removed the boundary conditions from the equation and made them source terms.
You can think of it like that.
Okay.
I
Is it
guess.
a wrong way to think of it?
Huh?
Is it wrong to think that way?
So in many type of discretization, you can move certain types of boundary conditions into the right hand side, right? And perhaps you can think of it as an equivalent of some kind of a delta function near the boundary, right? So maybe you can think of it like source terms that way, right? Perhaps you can think of it being equivalent of having like a delta function in the source term on the boundary. All right. Okay, so this is a Dirichlet boundary condition. If you have a two-dimensional domain and you have a range of more than 2 points, right, infinite many points, then you may have many of these known values at the basis functions. And you need to move a lot of columns to the right-hand side of the matrix.